There is an urgent need to address the extremely high levels of atmospheric carbon. As you can see from the data recorded at the Mauna Loa Observatory, atmospheric carbon levels have been steadily on the rise since the Industrial Revolution, with no sign of stopping. And rising levels of carbon dioxide are a key driver of the climate crisis we are experiencing today. Some effects of the climate crisis include heat waves, ocean acidification, droughts, melting glaciers and rising sea levels, more devastating natural disasters, and a greater loss of life, not to mention the financial burdens this crisis places on people, communities, and governments. Our planet cannot recover from this much carbon all at once, and we need to mitigate the effects of the climate crisis. To help our planet out, that's where MACS comes into play. So hello, we are Team 4. I'm Jamie.
I'm Haley.
I'm Sachi.
I'm Nadia.
I'm Licha.
And our senior design project focuses on developing a minimally adapted carbon sequestration cell, or MACS for short. Using principles from genetic engineering and synthetic biology, we seek to create a more efficient way to capture carbon dioxide from the atmosphere by using a carbon fixation system that works in vivo.
Meet the POAP cycle, a synthetic carbon fixation cycle designed to be compact and efficient, perfect for modern bioengineering. Instead of relying on complex, slow, or inefficient natural cycles, POAP offers a streamlined approach to converting carbon dioxide into key cellular building blocks, with fewer enzymes, less waste, and more control. Best of all, it's self-sustaining. Once active, the cycle regenerates in its own intermediates, allowing continuous carbon fixation without constant input of external metabolites. Not all carbon fixation pathways perform equally, and when compared to natural pathways like the Calvin cycle, POAP offers clear advantages. The Calvin cycle relies on rubisco, a slow and error-prone enzyme that often grabs oxygen instead of carbon dioxide. POAP avoids that bottleneck entirely, using faster, more precise enzymes. It also runs on fewer, more versatile cofactors like ATP and ferredoxin, making it significantly more energy efficient. And unlike the Calvin cycle, which loses carbon through photorespiration, POAP captures and recycles every carbon atom it fixes. Bottom line, POAP is a synthetic upgrade, smarter, compact, and more efficient.
Here's an overview of the project's workflow. Work started by using a database to search for feasible enzyme variants. Then we cloned the genes, creating two plasmids that each had two enzymes. These sets of two enzymes were inserted into the minimal cell, and gas chromatography mass spectrometry was used to test enzyme functionality. Finally, all four enzymes were added to one plasmid and inserted into the minimal cell. Here are a handful of the enzyme variants we had to choose from. Note that each enzyme is functional at a different temperature. In bold are the variants we selected, but 3 of the 4 work at temperatures higher than 37 degrees Celsius, where the minimal cell grows best. Overcoming this required thermal adaptive laboratory evolution, or TALE, to adapt the cells to growing at higher temperatures. By slowly raising the temperature and passaging only the cells that survived each increase, we created a minimal cell strain that survived at over 44 degrees Celsius.
The JCVI minimal cell, SYN3B, is the perfect vehicle to hold the synthetic pathway due to its small genome of less than 10 kilobases. It only contains the genetic information required for cell division, and therefore there are not many other metabolic pathways that would interfere with our inserted pathway, therefore making it a great candidate to hold our vector. To test the function of the enzymes, we first divided the pathway into two parts. Part A containing enzymes ACS and P4, and Part B containing PYC and OAH. We expect Part A to consume acetate and produce pyruvate, and we expect Part B to do the opposite, consume pyruvate and produce acetate. We tested for the expected produced metabolites using GCMS.
We then worked on creating our final 4-enzyme construct, which contains genetic information for all of the enzymes, and we obtained successful sequencing results.
Now that we have successfully inserted the full 4-enzyme construct into the minimal cell, the next step is to confirm the functionality of the pathway in the cell. First, we plan to use GCMS to detect pathway intermediates. Next, we plan to measure carbon fixation to determine how much carbon the POAP pathway sequesters in vivo. Finally, for future scalability, we plan on developing a minimal media and coming up with a sustainable solution to the POAP cycle's oxalate byproduct. These steps help confirm the functionality of MACS and its viability as a solution to climate change. And finally, we'd like to thank our mentors, Dr. Yo Suzuki and Radisha Kumar from the J. Craig Venter Institute for all their help and guidance on our project. We'd also like to thank our collaborator, Dr. Immo Burkhart from the Moore Lab at Scripps Institution of Oceanography for all his help with GCMS. And finally, we want to thank the UCSD Department of Bioengineering for all of their support. Thank you.